me get recording started and share screen, full screen. Do you see it? Okay, good. So let me get started. So this is week 2, and we already started creating. And so you're already seeing quantum field theory. So, you know, it's a rapid progress you're making already. So we made this huge jump. And conceptually, I know it takes a while to sink in, but using these creation-annihilation operators we are familiar with in harmonic oscillator and quantum mechanics, we now regard the creation operator as an operator that can create a particle, literally. And in this case, this index n refers to a possession. So what we started doing is look at the case of this 1D lattice, and the vacuum state is the state where you don't have any particles in the system. So, but the definition of the vacuum state is a state that is annihilated by annihilation operator at every site of this one-dimensional lattice. So AN is an annihilation operator, N refers to a particular site. And this condition tells you that there is no particle here. And this should be satisfied for every n, so that this is the state where there's no particle in site 1, there's no particle in site 2, So that's the definition of what we call the vacuum state. And once you have this vacuum state, you can literally start creating, namely that you act this creation operator on this vacuum state at a particular site, in this case, site number 6, so that this is the state where you have a particle at site number 6. And you can keep doing it. Now I created another particle at site number 14, another particle at site number 2, another particle at site number 11, and so on and so forth. So this is the way you can keep creating more and more particles. And one thing I emphasized on Wednesday is that you can freely interchange the order of these creation operators because they commute. What that means is that this state is automatically symmetric under interchange of 3 particles in this case, at site 2, site 6, site 14. So if you interchange particle at site 2 and site number 14, the state doesn't change, which means that this is the state that is automatically symmetrized under any interchange among particles, which is the wave function of the boson, as you must have seen in multi-particle quantum mechanics. So that's something you find here. And so far, we only just took a collection of harmonic oscillators at every site. So corresponding Lagrangian, as you're working out actually in a homework problem, is this form for every site. And you just sum up the Lagrangian at every site at the end of the day. And correspondingly, Hamiltonian is also a Hamiltonian for a single harmonic oscillator. And I'm dropping the constant term I'm not interested in for now. And you just sum them up over every site. So whenever you create a particle that costs you energy of h bar omega, each time you increase the number of particles, that costs you energy h bar omega. So that's the Lagrangian and Hamiltonian you got so far. But I pointed out a problem with this because what we would like to describe eventually is a particle moving in a free space. And so far, once you actually place a particle at a given site, this is already the energy eigenstate. And energy eigenstate means that's a stationary state. So over time, system doesn't change, namely that the particle at site 11 in this case cannot move to site 12 or site 10. So these particles are in some sense infinitely heavy right now. And so what we would like to do is to give an additional term to the Hamiltonian so that we can make sure that the particles get liberated. So right now they are confined and encaged at every site. Now we let the particles move. So that's how we do it is the next slide. And we add additional terms to the Hamiltonian so that they can start to move around. So anyway, so this is the way I finished up on Wednesday. So do you have any questions about what we talked about so far on this? No questions? Everything okay? Well, if something comes up, do let me know. You can interrupt me anytime. So this is the Lagrangian that describes independent harmonic oscillator at each site. And it's just a grand sum of Lagrangian at each site. Correspondingly, Hamiltonian is also the grand sum of Hamiltonian at each site. And this was the cause of the problem, that the particles couldn't move, because once you create a particle at a given site, it just stays there forever. So what we need to do is to come up with a way of letting a particle move, let's say to the next site. So if you want to let the particle move from the site 6, so this is the state you start with. So you created a particle at site 6. Then you'd like to make sure this particle can hop to the next site, let's say site 7. So you need to find a way of letting particle change from this state, A6 dagger on the ground state, to this state, A7 dagger on the vacuum state. So how do we make that happen is the next question. And the answer is actually pretty obvious. What you have to do is to actually annihilate the particle at site 6 and recreate the particle at site 7. So, it may sound like a crazy idea. It sounds kind of cumbersome. Why do you have to go through this creation and annihilation each time? But, in harmonic oscillator, that's the only operators we got. So we use what we got. So the way to describe this motion of the particle is annihilate a particle at one site, and the particle created at the other site, so that actually describes how particle can move. So what you want to do is to add a term to the Hamiltonian that looks something like this. So here, this term is what I just described. You annihilate a particle at site 6. So this state has particle at site 6, this gets removed. Then you create a particle at site 7. So this particle now appears at site 7. So end result is that particle moved from site 6 to site 7. Then you have to add another term here to make sure that your Hamiltonian is Hermitian. So Hamiltonian is an observable, its eigenvalue has to be real, has to be Hermitian, and this term alone doesn't make the Hamiltonian Hermitian. So I add Hermitian conjugate of this term, which is A6 dagger A7. So what you see here is that this term, second term we added, would also let the particle move, but now in the opposite direction. You annihilate a particle at site 7, and you create a particle at site 6. So this term would describe the motion of the particle from site 7 to site 6 instead. So this is the way the particle can move in either direction from 6 to 7 or 7 to 6. So this is the term we are going to add to the Hamiltonian. As a result, your Hamiltonian not only has this harmonic oscillator piece we already had on the previous slide, but now we add this additional term so that particles can move around. And so far, there's no connection between the size of this h bar omega and this capital K, and I'm using capital K to sort of imply that this has something to do with the kinetic energy, and we get to that connection soon. So far, there's no connection between the two, but at the end of the day, we really would like to take what we call the continuum limit. So we take the limit where the distance from one lattice site to another, namely lattice constant, goes to 0. Then you have a continuous space. And what we want is that in that limit, this reduces to the Hamiltonian of a free particle. So that requirement ends up connecting this h bar omega and k. So right now, both of them look kind of abstract, and we don't know what they are really. But eventually, these numbers get connected to the mass and the momentum of the particle, so that this ends up really being the kinetic energy at the end of the day. So I go through this one step by one step. So if you add this term to the Hamiltonian, Lagrangian is AA dot minus Hamiltonian. So you need to be sure about the sign change. So negative K goes to positive K. So that's the Hamiltonian we are going to use. So before going to the continuum limit, any questions about this idea that this term in the Hamiltonian would let particle move now?
Why do we need the conjugate in the Hamiltonian?
Yeah, so we need a conjugate here because we need to make sure the Hamiltonian is Hermitian operator. So we learn in quantum mechanics that every observable, which you can measure as a physical observable, is of course real. Eigenvalued Hamiltonian is real. And by making sure that Hamiltonian is a Hermitian operator, it's guaranteed that its eigenvalue is real, unlike the eigenvalues of the annihilation operator you saw on Wednesday, namely the coherent state, where eigenvalue can in general be a complex number. So the rule is that if you want to make sure that eigenvalued operator is always real, then you need to make sure that the operator is Hermitian, and the second term guarantees that Hamiltonian is Hermitian, while non-Hermitian operator, like an annihilation operator, can still have a real eigenvalue, but can also have a complex eigenvalue in general. And so that's the major difference between Hermitian and non-Hermitian operators. So thank you for that question.
Okay, thank you.
And
I
can't see your name, Natalie. Okay, Natalie, I try to remember that one. Yes, another question.
So that extra term you add, could you like think of it as like a bosonic like product state of like the two nodes? It looks kind of similar to like how we talk about like bosons and like two positions, or like, you know, a shared wave function.
Superposition among what kind of states do you have in your mind?
Like if you have like two bosons in like one wave function, you can represent it with like the two positions being like swapped with like, and then like a plus sign.
Mm-hmm.
Like it looks kind of similar to the form. Like, can I think of it that way? I guess we haven't seen like fermions yet.
Yeah. I'm afraid that is different. So what you're saying actually corresponds more to what I discussed on the previous slide. I have to go back now. Namely that once you actually have these multi-particle states, then this is where you can interchange particles. And there's always a plus sign because nothing changes. So that's a symmetrization of the wave function of the bosons in the language of QFT. So it has to do with this multi-particle state that actually leads to the quantum statistics of Bose-Einstein statistics in the case of course, bosons. And that is different from this Shakespeare operator we are talking about right now. Does that answer your question, Cameron?
Yeah, thank you.
Okay.
Oh, I had another question.
Go ahead.
On this slide. So this Hamiltonian looks very similar to the Hamiltonian that you see for like the 1D Ising model. Is there any connection between like this, between what we're studying here and the Ising model?
Yeah, there is. So in the case of Ising model, of course, you are allowed to have only two states at a given site. So in some sense, Ising model is a fermion. You can have spin down state and spin up state. And then you can have the nearest neighbor interaction. So you can write a Hamiltonian like this one. So it turns out that Ising model in the continuum limit really does reduce to a theory of free fermion. And at the critical temperature becomes a massless fermion. So this is one of these amazing connections that you can think about these condensed matter systems like Ising model. And once you try to go to a QFT description of that system, then you take the continuum limit near the critical point, and description tends to become actually very simple. So this complicated interaction of nearest neighbor simply just turns into a massless fermion theory at the end of the day. And we are not talking about fermions right now, we are talking about the bosons, but we get to talk about fermions later. So if you're curious, you can ask that question at that point again. That's an excellent question. Any other questions?
Just a quick one about the Hamiltonian Lagrangian with regards to this motion term. The fact that there is an an+1 little bit implies that there is some motion between a state that is defined as n and n+1, even though we have only n states. Is this intentional? Or
no, this n, I'm sorry, this n doesn't refer to n state in the sense of number operator. This n refers to a site. So this is a term, you annihilate a particle at site n and create a particle at site n+1, so it moves to the right. And this is a term that annihilates the particle at site n+1, create a particle at the site n, so particle moves to left. So in each of these terms, the total number of particles is conserved. So this one annihilates a particle and create at the same site. So this is the energy associated with the particle sitting around. This is the term that is associated with the energy of the particle moving. But again, in each of these terms, you annihilate one, you create one. So you are never changing the number of particles with this Hamiltonian. So far, we are not discussing a system where number of particles changes, which is sort of in some sense the ultimate goal of QFT. But so far, we are not actually changing the number of particles yet in the Hamiltonian. So once you have one particle state, this Hamiltonian would keep it as a one particle state. The only difference is that now it can start to move. Am I addressing your question, Earl? Okay, go ahead.
I'm more directly asking about the fact that since we're summing over all states n, this implies that there is a site n, wherein if you go to the last term of the sum, an would be the last site and n plus 1 would be some additional site beyond the last site if you did this full sum.
That's the question you're asking. Okay, I apologize, I didn't understand. So you can either imagine that this lattice is infinitely extended so that you don't have to worry about the boundary, or if you like, you can impose a periodic boundary condition that if you go to, let's say, capital N, you go back to the original state. So either way, you can just pretend that this sum extends in a either periodic or infinite sum so that you don't have to worry about this issue about the boundary.
Okay.
Is that okay?
I believe that addresses, yeah, that addresses my question.
Yeah, thank you for asking that question. Any other questions here?
Oh, I had one other quick question. So the constant term that we kind of neglected in the Hamiltonian, is the interpretation of that term just like the vacuum energy?
That's right. So,
okay.
So the state that doesn't have any particles in it is the state I call the vacuum. And if there's a constant term in a Hamiltonian, that state with no particles would have a constant energy. And this is actually one of the biggest problems in the modern physics, namely that the vacuum seems to have an energy, and that's what our soul Perlmutter discovered. Universe seems to be accelerating, and this is crazy. So if the universe started like a big bang, everything starts to spread out, but the gravity would only pull, it never pushes. So the gravity will put the brake on the expansion. So the expansion, we believed, was supposed to decelerate. It was supposed to slow down. But Saul discovered that the universe is actually accelerating. It's speeding up its expansion. So what that means is that something is pushing the expansion from inside. So in some sense, you may call that anti-gravity. And what is pushing, I don't know yet. And that is what is called the dark energy in general. And one possibility what the dark energy may be is the idea called the vacuum energy. So if vacuum, nothingness, has a energy, constant energy per volume, as the universe expands, the volume gets bigger, so you end up having more energy. So that's an infinite source of energy. So that sounds really crazy, but just imagine such a thing exists. Then Einstein told us in the general relativity that the way universe expands is really dictated by what's inside, namely that how much energy there is inside the universe tells you how fast the universe must be expanding. So if this dark energy keeps multiplying, that ends up pushing the expansion to make it go faster and faster. So at least that's a description of why universe may be accelerating. And there's still a lot of precise measurements we intend to do. I myself is involved in a measurement at the Subaru telescope and trying to measure the expansion rate of the universe as a function of time more precisely to see if this idea of the vacuum energy really makes sense or not. And that's one of the biggest problems in physics today, what exactly this vacuum energy is. So constant term, I'm dropping it because here I'm not talking about gravity, but once you introduce gravity, even constant matters. And that is the idea called the vacuum energy. And that's a subject of intense interest. So that was a great question, Miguel. Thank you. Any further questions? Okay, so let me go to the next slide then. So far we introduced these different terms in the Hamiltonian, and they are not related to each other. But by using the requirement that this reduces the free particle in the continuum limit, we would like to actually fix them and relate them to basically mass and momentum of the state. The first thing we like to do is to consider this linear combination of states of particles at different sites. So you can see that this is sort of the analog of the plane wave state. Once you notice that this n times d, where d is this lattice constant, basically talks about the position of the particle on this one-dimensional space, right? So nd ends up being x at the end of the day. So this is e to the ik x. So that's the wave function of a plane wave. And this is actually what people do in condensed matter physics without taking the continuum limit, because you would like to describe, for example, electron hopping from one atomic site to another. So this is actually literally the Hamiltonian people use in condensed matter physics. And also this state is again literally what the condensed matter physicists use to describe an electron moving on this lattice. So even without taking the continuum limit, this expression already has a practical use for it. But anyway, here we are interested in continuum limit. So we end up taking the limit where this d, the lattice constant, goes to 0. But before doing so, it is actually a useful thing to check that this state I just introduced by taking a linear superposition of states at different sites is actually an eigenstate of the Hamiltonian we just talked about. So let's actually verify that. So all we have to do is that we got this Hamiltonian we introduced on the last slide, and let this Hamiltonian act on this state with a linear superposition of the states particles at different sites. We are still talking about one particle state, just a reminder, and we just act this Hamiltonian on it. Then that's easy to do, right? So if you have a particle at site M, the only piece that contributes for the first term is when you annihilate the particle at site M. If this n is a different site, then this an and am dagger would commute, and then an is acting directly on the vacuum state, and by definition, vacuum state gets annihilated by the annihilation operator, so that's 0, so it doesn't contribute to the result. So the only case when this term does contribute to the result is when this annihilation operator refers to the same site M, so that you have vacuum state, creation operator am dagger is acting on it, and then this am annihilates that particle, and then recreates the particle at the same site M. So that's this first term here. So we started out with the sum both over n inside the Hamiltonian and m inside the state, but the only piece that remains is when n and m are the same. Hence, this first term over here is directly acting on the vacuum state. And then we look at the second term. It's the same story, only when this n is the same as m that contributes to the final sum. So I have am dagger that gets annihilated by am now. Then you create a particle at m plus 1. So you find this am plus 1 dagger contributing to the final result. So that's the piece here. And the last one, again, you need to make sure that this annihilation operator annihilates the particle where it exists. So m, in this case, has to be same as n plus 1. So n is m minus 1 then. So you annihilate a particle at site m and end up creating a particle at site m minus 1. So that's the last piece in the second line. So it's easy to act as Hamiltonian on this state, which is an infinite linear superposition of particles at different sites, but you can actually work this out this way. Then I do a little bit one step of massaging to make it clear this is the Hamiltonian eigenstate. So because this sum can be separated into 3 pieces, and m is a dummy variable for this sum, I'm allowed to change what dummy variable I use for this sum. So the first piece is I don't have to change anything about this dummy variable m. I just let this am dagger acting on the vacuum state. And I'm keeping this, the exponential factor next to this h bar omega. So here I just reshuffle the ordering of the factors I have for this state. So here I haven't done anything. But for the second term, I relabel my dummy variable m by m minus 1, so that this a dagger m plus 1 becomes the same as am dagger I got from the first term, so that I can put them together into the single expression. So that's why I'm changing this dummy variable m for the summation to m minus 1. And now that this creation operator refers to the same site m, am dagger. But by doing the change of the dummy variable, this m in the exponent should be replaced by m minus 1. So the exponential factor I have is now e to the ik m minus 1 d instead of ik m d. So that is something I have to be careful about. But again, I haven't changed anything. I just replaced the dummy variable m by yet another dummy variable m minus 1. And I play the same trick for the last term. So here, once again, I would like to make this am minus 1 dagger to am dagger so that I can put them on an equal footing. So that requires me to change this dummy variable m to m plus 1, so that m plus 1 minus 1 is m. Then I have this am dagger, so all the three terms are now together in this big parentheses. But once again, I have to be careful that this m in the exponent is replaced by m plus 1. But anyway, so this is the way I rewrote everything in terms of this single state am dagger acting on the vacuum state with this multiplicative coefficient in front of it. Then this plus that is actually simple cosine. So if you actually factor out e to the minus ikd from the exponent and e plus ikd from the exponent here, they sum up to twice the cosine kd. Then I separate out e to the ikmd from both of these terms, which is the common term from the first term as well. So that factorizes out of this big parentheses. So I get am dagger times e to the ikmd. And that is nothing but the initial state we started out with. So e to the ikmd factor times am dagger acting on a vacuum state summed over m returns us the state k we wanted to study. So now you see that indeed this state k is an eigenstate of the Hamiltonian. So acting Hamiltonian on the state k gives you a number in front of the state k, where number is given by h bar omega minus 2k cosine kd. And this is where we can think about the continuum limit. So if you choose, now I'm putting together this relationship between these two parameters, if you choose h bar omega to be 2k, then this becomes further simpler to just 2k times 1 minus cosine kd. And the reason why this choice makes sense is that once you actually take in a limit where d goes to 0, 1 minus cosine kd turns into k squared d squared over 2. So that cancels a factor of 2. So you find something that is quadratic in k. And there are, of course, higher order pieces in d, but when you send d to 0, then those terms become negligible. So this quadratic term is a dominant piece. Then you find something that is proportional to k squared. So in addition to choosing h bar omega to be 2k, if you further choose k to be h bar squared over 2md squared, then this eigenvalue of the Hamiltonian turns into h bar squared k squared over 2m. Now things start to look familiar. This is nothing but the energy of a free particle, p squared 2m, where in quantum mechanics, momentum is given by h bar times the wave number k, and that's a Dubois relation for a matter wave. So if you choose h bar omega to be 2k, if you further choose k to be h bar squared over 2md squared, you expect that this Hamiltonian on one-dimensional lattice would reduce to a free particle on a continuum space by taking the limit where d goes to 0. So we started out with this 1D lattice because we can use this harmonic oscillator on each side using the language we're familiar with. But now we are approaching the quantum field theory in the sense that this AM turns into the annihilation operator at position x equals nd. And AN dagger turns into a creation operator of a particle at position x equals nd. So by taking the limit d goes to 0, this whole Hamiltonian now turned into a Hamiltonian on the continuum space. And choosing h bar omega and 2k in this following fashion, we expect that this would give us Hamiltonian and Lagrangian of a free particle moving in free space. So that's what I'm going to do on the next slide. But anyway, so this is how you think about how you actually take the this plane wave state to be the eigenstate of the Hamiltonian. And by making sure that the eigenvalue turns into the familiar form of p squared of 2m, we could relate these parameters omega and k to something we know, namely mass of the particle. And then you know how to take the continuum limit so that you can find the correct Lagrangian of a free particle moving in a continuum space at the end of the day. So that's the strategy we are taking. And just in case that you're getting a little lost in thought, what we're trying to do here is to really build up quantum field theory bottom up using the algebra of the harmonic oscillator. And most textbooks actually don't do this. They do top down. You are being handed the Lagrangian or Hamiltonian of the QFT, and they ask you to quantize it. And then somehow on the way, you'll find that that ends up describing a free particle. And so that comes out to a big surprise. So here, I'm trying to minimize the suspense by trying to build a QFT bottom up by something you know from the quantum mechanics, and you're trying to create a quantum field theory Hamiltonian out of scratch. And this is the way you can discover quantum field theory on your own. So that's the approach I'm trying to tell you right now. Okay, let me stop again to see if there are any questions. I'm sure there are.
Yeah. Professor, could you please explain how we got rid of AN in the second line?
This one?
Yeah.
Yeah. So thank you for the question, Andy. So the idea is that here we have sum both over m that describes the state I prepared and sum over n that is part of the Hamiltonian. But the only way the A term would survive is when this AM dagger and annihilation operator refer to the same site. So if this A annihilation operator and creation operator A dagger refer to different sites, then I can commute A and A dagger, then A acts directly on the vacuum state, which is by definition 0, being the vacuum. So only way this term would survive is when this M that refers to site M, and for example, this n plus 1 that refers to site n plus 1 are the same sites, then n plus 1 has to be M that reduces one of the sums. So sum over n is now gone. And then I'm supposed to take n to be m minus 1 so that n plus 1 refers to the same site M. And then AN dagger turns into a m minus 1 dagger. And that's the term that survives in the end. So that's how I got rid of the sum over n, but the sum over m is still there. Did I answer your question, Andy?
Yes, thank you very much.
Any further questions?
Professor?
Yes.
From the line 2 to 3, when we when we play around with the index m, That's only possible because the summation is from negative infinity to infinity, right?
Yeah, that's an excellent point too. So as we're trying to respond to the previous question by Earl, you can either regard this n to be summed from negative infinity to infinity, then changing this label doesn't change the sum, or make it periodic. So if you actually change m to m minus 1, the whole period, that's a circle, would move by 1 unit, and that's still the same sum. So either way, you don't have to worry about this issue with the boundaries.
Oh,
Does that answer
okay,
your
thank
question?
you.
And your name is Jia?
Oh, Jiu.
Jiu, okay. Sorry, I can't
thank
read it
you.
on this Zoom. Okay, all right, good question, Jiu. Anything else? Is everything okay? All right, so now we really would like to take the continuum limit because we identified how we need to choose the parameters in this Hamiltonian. So here's the Hamiltonian. Now we know h bar omega is 2k. K is h bar squared over 2md squared. So I just literally substitute that in. So this h bar omega then is 2k. So I have this h bar squared over 2md squared up front, and this factor of 2 remains. So the first term is 2 an dagger an. And for the second and third terms, this capital K is this coefficient up front. So there's no factor of 2 here. So I have minus an plus 1 dagger an, minus an dagger an plus 1. And I realized that I switched the notation once again. So this n was what used to be m on the previous slide, I guess. So this is the Hamiltonian now we believe should have the correct continuum limit. So how do we take this limit? Well, first of all, we put this Hamiltonian into Lagrangian once again. And Lagrangian has the sum over the sites n. And then continuum limit is defined by taking this lattice constant to 0, so that what used to be the lattice, now you see at the top of the slide, is now is a continuous line where particle is supposed to move. And then what we know from probably calculus class is that sum over n times the interval d would have a limit of reducing to an integral over the possession x. Maybe a little bit more familiar expression may be that sigma, the sum of delta x, reduces to integral dx. So the sum over very fine lattice is the same thing as integrating over the possession. So that's the idea we're going to use. So this sum over n over every site now reduces to an integral, but there is this factor of d we have to be careful about. At the same time, we also need to take a proper limit of this an, annihilation creation operator, to become a function of possession x. And for this purpose, it turns out that you need to factor out this factor of d to the 1/2 so that I can have a correct limit. And the reason is very simple. All of these terms have 1 power of a and 1 power of a dagger. And in order to reduce this sum to an integral, then I need this factor of d in here. To get this factor of d out of this expression in the sum, I need to factor d out, and therefore I need to extract half power of d from an, half power of d from an dagger, and that's why I need to write this an after factoring out the power of d to the 1/2 power, and the rest is quantum field that appears in quantum field theory at the end of the day. So this is the way I rewrite annihilation operator in terms of psi, that is now the quantum field in full glory. So I just make the substitution to write an as d to the 1/2 psi, an dagger to the d to the 1/2 psi dagger. So here's the rewriting. Then I factor d out, so that d together with sum reduces to the integral. That's the integral I have up front here. And the first term is psi dagger, and an dot becomes psi dot. That's the time derivative, right? According to Newton's notation. So now we know what the first term is. IH bar psi dagger of x, psi dot of x. And once again, psi is now a function of the continuous space parameterized by x. And because psi is a function of space, this is a field in a similar way that electromagnetic field is an electric field as a function of possession of space. Magnetic field is a function of the possession of space. So in a similar footing, this psi is now a field. Namely, the creationization operator we define at every site on the lattice became this field operator, which is a function of space. So this is just taking the limit of infinitely small lattice spacing, and that's how you get this quantum field now. And what you see in the textbook you have is starting with this, and then quantize it and get the free particle in free space. So here now we are actually building it up in a bottom-up fashion. And we will do it also in top-down way after this, so that you see the connection that you can start with the lattice and recover the continuum limit, or you can also go from continuum space and then go to the lattice and then and find the Hilbert space and so on and so forth. So you can take limits in either way, but anyway, that's the way you find this first term. Second term is a little tricky because that involves the difference of creationization operator at different sites. And by taking a continuum limit, you can expand a dagger n plus 1 in Taylor series in terms of the lattice constants. So n plus 1 refers to the site x plus d. So that's the next site separated by distance d. And the difference between them at the first order in d is given by this derivative with respect to the possession. So what you do is write this an plus 1 dagger as psi dagger at x plus d. And when you expand this, the first order term is psi dagger of x, which cancels the first term in the parentheses, which has psi dagger at x, except for the factor of 2 that is canceled by the second term over here. So because the zeroth order term in d is canceled between the two, what remains is the first order term in d. That's this derivative. And you do the same thing also for this an plus 1 dagger. And you have to do this expansion up to the second order in d. And if you do that carefully, then it turns out that this whole thing in the parentheses turns out to be order d squared, because order d to the 0 term cancels, order d term also cancels, and then at the end of the day, what remains is order d squared piece, and d squared times the derivative of psi dagger and derivative of x is what remains at the end, and d squared cancels this d squared in the denominator in this constant capital K, so d dependence would disappear from the expression. Then you find this term, which is grad psi dagger, grad psi. So that's how you take the continuum limit out of this Hamiltonian or Lagrangian on the lattice. And you also need to take the limit of this creationization operator commutation relations. Am dagger used to be Kronecker delta. Now this n and m got promoted to a continuous possession x and y, and the Kronecker delta becomes a delta function in space, delta x minus y. So now we have this Lagrangian with this commutation relation between field operator psi of x and its Hermitian conjugate psi dagger of x. And together, this is now supposed to be the quantum field theory of a free particle moving in free space of one dimension. So I hope at least the steps are clear. And again, I stop here and wait for questions from you.
When doing the converting the A's to the psi's. Maybe I didn't follow it exactly, but why are the two gradients multiplied together rather than just being two things you subtract by?
That's an excellent question too. So if you actually want to do the theta expansion in steps, here I have psi x dagger, psi x. Here I have psi x plus d dagger, psi x. And here I have psi x dagger, psi x plus d. Then you start doing the theta expansion. And for example, this, from the last term at order d squared, psi of x plus d has psi of x as a 0th order plus d times grad psi as the 1st order plus d squared over 2 times the psi double prime x, the second derivative. So second derivative is there too. But because this Lagrangian is meant to be integrated over space, once again, I'm dropping total derivative and allowing myself to do the integration by parts by dropping the boundary term. So in response to the previous question by Earl, the boundary term, of course, is not there if this is actually a periodic boundary condition so that there's no boundary. Or if you think this of the infinitely extended space, then we don't care about what's going on at infinity in the universe. So you're not worry about what's going on at the boundary term. So either way, I'm allowed to drop the boundary term. And then second derivative times field can be converted into first derivative times first derivative. So if you just write this out in gory detail, then you really do see that this reduces to this term. And that is what I actually intend to be part of your second homework problem. So all you need to do is to literally just theta expand the field up to the second derivative. And you can see that how things cancel against each other. And then second derivative on the field would be converted to first derivative using integration by parts. Then all terms end up being of this form at the end of the day. And you will verify that yourself in the new homework problem. I hope that answers the question, Asha.
Yeah, it definitely did.
Okay, good. Any further questions? Everything okay? All right. So now this is the moment you finally have seen a quantum field theory in full glory. So quantum field theory of non-relativistic particle is described by this Lagrangian. And if you just take the second term alone, that is the Hamiltonian of the quantum field theory of a non-relativistic free particle. So all we have to do is to take this original Hamiltonian on the lattice and take this continuum limit. And here, what we really owe to is to Mr. Leibniz, who came up with all these notations, which is extremely useful, right? So we just use the fact that sum over all points times this interval among the lattice sites has a limit of going to an integral. And this symbol of the integral, if you look up the Wikipedia, originates from old symbol for S in German. This sigma was also meant to be S for summation. And summation was discrete, but now summation becomes continuous. And that's where the Mr. Leibniz has this ingenious idea that let's take this symbol S, it's called the long S in the ancient German script, and then use this and stretch that out to obtain this new symbol for the integral. So that was the idea. And this long S is no longer used in the German literature, but there is still remnant of this. If you have seen, for example, anything written in German, you might have noticed that there's actually an alphabet that looks like Greek letter beta. It's not beta, it's called SZ. But this actually is a combination, the compound letter made up of this long S and Z, which is Z. And if you put them together, that kind of looks like beta, and that's the origin of this funny letter called SZ. So if you look at, for example, the street name in Germany, you see Straße. This is this SZ, which is pronounced like a hard S in English language. And the reason I know it is actually I grew up part of my childhood Germany. So I lived in what used to be West Germany, still a divided country during the Cold War. And I actually had an opportunity to visit Eastern Berlin and have seen the Berlin Wall. And it was really tragic. This is the famous street called Bernauer Straße. This is a street where this an apartment complex ended up becoming the wall. And people living in these apartments threw themselves on the street to escape from the east side of Berlin to west side of Berlin, and a lot of people died. So I actually had visited that location, and so it was a pretty big shock for a little child to see really the horror of the Cold War in front of my eyes. And I did have a chance to also go into Eastern Berlin, and Western Berlin was very sort of vibrant, typical Western city. But the minute I go into the Eastern Berlin, the first thing you see is the minefield, watchtowers, and there were still ruins from World War II, even though that was already in 80s. And then start the buildings of this old Soviet-style gray concrete buildings. It was a huge contrast between West and East. But anyway, so this is the reason I know something about German, and I know that this beta-like symbol is pronounced S, and this part of this symbol is this long S, which ended up being this symbol for the integral. So this was the ingenious idea by Leibniz. And that's why we can use the symbol like dx by dt as a symbol for derivative, and the chain rule becomes very simple. dz dx is dz dy times dy dx. You can pretend that dy cancels between the two terms. And also the integral of total derivative just recovers the original function. Again, you can pretend that you cancel dx, and so that it becomes just f. So all of these, nice looking notations are thanks to Leibniz. And compared to Leibniz, Newton had this awkward notation of time derivative being dot, second time derivative being double dot. We still use it. We used it on a previous slide, but it doesn't have sort of the beauty or elegance of the notation by Leibniz. But of course, we still respect Mr. Isaac Newton because he is the one who invented the equation of motion and as the universal law of gravity. So we owe also something to Newton as well. And they lived in the same era. So apparently, Newton and Leibniz had a bitter war about the credit on who invented calculus. And according to Wikipedia, this is actually a complicated story. So Newton actually wrote this famous book on the calculus already in 1671, but for some reason he didn't like it for a while and published it only in 1736. But in the meantime, Leibniz already published his manuscript before Newton published in 1675. But this manuscript was written after Newton wrote the manuscript at the beginning. So in some sense, both of them have claims to have the credit on the invention of calculus. And you might know this, but it turns out that around the same time, there was also a mathematician in Japan named Takakazu Seki, and who lived literally in this era. And he invented calculus also totally independently from either Newton or Leibniz, because there was basically no communication between the West and East back then. So, who gets the credit? I don't know. I guess all of them should get a credit. But in some sense, this was the good old days. These days, information travels with speed of light over the globe. So, waiting for a couple of years is a disaster for you if you want to claim a credit. And this is one example I experienced myself, what a modern competition looks like. One of my best cited papers, called Anomaly Mediation Supersymmetry Breaking, is something I wrote back in 1998. And that was based on a collaboration among 4 of us. So I here on the West Coast, another guy, German guy on the East Coast at Maryland, and the 2 Italians living in Switzerland. So that was a collaboration of 4 members. And we have written the paper more or less, but we were meeting at CERN, we got together and started the work. But after we all went home and I started to teach and everybody got kind of busy, so the draft was sitting on a computer and it was not quite finished. But one day I was checking the archive on the internet. And as some of you might know, the papers appear on the archive in the evening on the West Coast. And when I was checking it in the evening before going to bed, I found a paper by Lisa Randall and Raman Sundram. The Lisa Randall from Harvard, Raman Sundram from the University of Maryland. That paper appeared on the archive, which had almost exactly the same result. So I panicked. And so I emailed my friends right away. And then my friends in Switzerland was just about to wake up. So they told me, well, of course, we already have a draft ready. So why don't we try to finish this in a day to make sure that everybody knows that that's an independent piece of work? And it's really late for you, so go to bed. And we start to write and try to finish the paper. So they start to work in the West Coast, in Switzerland. So these two, Gian Giudice and Riccardo Rattazzi, start to finish up the draft. And they didn't quite manage. And the draft was sent to my other collaborator in Maryland when he starts to come into this office. And he kept on writing. At the end of the day, he handed the paper to me. And then I submitted it to the archive the next day. So that's how everybody in the community was convinced that this was indeed independent piece of work. And so maybe I didn't have a tenure if I hadn't worked very hard on that day. So that's how a modern competition looks like. So if you have a manuscript, wait and sit on it for 40 years, you wouldn't cut it in the academia these days. But anyway, so this is just a side story. But this is how we can actually make use of this wonderful notation by Leibniz. So it makes sense to take these continuum limits in an elegant notation. And I hope that gives you an idea that how we can get the quantum field theory Lagrangian at the end of the day. So here we really relied on this Leibniz notation. And now we have this the Lagrangian for the quantum field theory. So this is where you're supposed to rejoice. Now you see quantum field theory. Okay, let me stop here again and I can take questions.
I want to know if researchers ever get bitter if not what happened to you, but to the other researchers, because they posted their paper and then less than 24 hours you posted your paper. Mm-hmm. And I mean, does that like...
Yeah, everybody cites both papers. So the community, of course, tries to be fair. And once you see papers that are published from independent work, then everybody does cite both papers. And for some reason, I never understood. This kind of competition does happen a lot. Somehow similar ideas seems to emerge in the minds of totally different people around the same time. And I see many of these examples that two papers appear on the same day or just a couple of days apart from each other on the archive. And it's very strange, but it does happen. Maybe human beings does have this telepathic capability of communicating in an invisible fashion. I don't know, but this does happen a lot. And we try to be fair every time to pay attention and cite papers or all papers that appear around the same time, as long as they are independent. And in our case, of course, there was a big overlap between the contents of two papers, but there are parts that are actually sort of separate, unique to each paper. So whenever people try to cite a content which is in only one of the papers, but not the other, again, people try to be careful to cite that particular paper, not the other one. So that's the way, academic community tries to be very fair and even. So that's an excellent question. So that's the ethical issue in academia, indeed. Is that the question you wanted to ask? Was it Natalie? Oh, I don't hear from her anymore. I hope I answered your question. Okay. Any other questions? Everything clear? Okay. So now we do have a Lagrangian or component field theory. So this is the theory we actually call the Schrodinger field. The reason for that is because of the equation of motion. So here I have Lagrangian. Second term with the opposite sign is the Hamiltonian, and we have this commutation relation. And the way we use it is that once again, we have this vacuum state. And the idea is that when you act psi of x, which is now the continuum version of an annihilation operator, then it vanishes. So psi of x is the annihilation operator at position x. So if you acted on a vacuum state, then it annihilates the state. Then you can go to one particle state by using the creation operator as a function of position x1. So this is a state where a particle now exists at position x1. Then you have a two-particle state where you created particles, the first particle at position x1, second particle at position x2. But these are identical particles because psi dagger at different positions commute with each other. So even if you interchange the order, which corresponds to switching x1 to x2, it doesn't change. Therefore, two particles created by the same field are identical particles. They are different positions, but they are identical particles. Similarly, for the three-particle state of identical particles at positions x1, x2, and x3, four-particle state with identical particles at positions x1, x2, x3, and x4, and so on and so forth. So the idea didn't change from this harmonic oscillator case. Psi is the annihilation operator, psi dagger is the position operator. The only difference now is that both creation operator and annihilation operator comes with an argument, where the argument refers to a position in space, and we use them the same way we did before. And then we call this psi of x a quantum field. It's quantum because it's an operator, because it's an annihilation operator. And we call it field because it's now a function of x. So psi of x is a different operator depending on where you are in space, and that's the idea of a field. And by putting those two words together, we call psi of x as a quantum field. And now that you have a Lagrangian, you can derive the Euler-Lagrange equation. And Euler-Lagrange equation turns out to be this, namely that Euler-Lagrange equation is a stationary condition of the Lagrangian with respect to infinitesimal variation. So if I take the variation with respect to psi dagger, then the coefficient of the variation is IH bar psi dot. That's the first term in the Euler-Lagrange equation. For the second term, I take the variation of psi dagger, and in order to isolate delta psi dagger together with the delta psi dagger over here, I do the integration by parts once again. So this derivative would act on psi and turn that into the second derivative. And so I find this second term over here. So that's how I find this Euler-Lagrange equation. It looks like I have made a sign error. This must be plus after doing the integration by parts. So I'm going to correct that when and repost the slides later on. And so this is the Euler-Lagrange equation for the field operator psi. But now you recognize that this looks exactly the same as the Schrödinger equation for the wave function of a free particle. So this resemblance of the Euler-Lagrange equation for the quantum field to a Schrödinger equation of a free particle is the reason why we call this Schrödinger field theory. But you have to be careful here. Psi is not meant to be a wave function. Wave function is a C number. It's just a function. It's not an operator, right? But psi of x here is an annihilation operator. So this resemblance that the equation looks the same as the Schrödinger equation is actually misleading. It was so misleading that people called the field theory as the second quantization, which is even more misleading. So the idea of the word second quantization is that when you start with a classical particle, if you quantize it, you find the wave function psi of x. Then you take this wave function, quantize it the second time, so the psi of x becomes an operator. And that was the sort of rationale behind the name second quantization, but that's not what we are doing here. You saw the psi of x was throughout this discussion always just a continuum version of the annihilation operator. I never did anything second time. This is still the first quantization. So resemblance is just a resemblance. This Euler-Lagrange equation of the field looks like this is the Schrödinger equation, but it's not. And I try to make it very clear as I go on what is actually the Schrödinger equation for the quantum field theory and why psi of x is not the wave function. I try to make it as clear as possible, but I'm just warning you that I'm sure this will confuse you at least once. But you have to get through this confusion and clearly separate in your mind what is the wave function, what is the field, and hopefully that becomes clear as we go on. But here, this is just a point of warning that this is the confusion you are going to face most likely. But nonetheless, the Euler-Lagrangian equation of a field is of this form, which looks as if this is a Schrödinger equation for a free particle. But anyway, so here I emphasize that psi dagger is really the creation operator of a boson, some kind of boson. Psi is the annihilation operator of that boson. And using the creation operator multiple times, you can have a multi-particle state of identical bosons. And that's the idea how we use this quantum field to describe quantum systems. Okay, I stop here again to see if there are questions.
When you derived the Euler-Lagrange equation, you used the derivative with respect to psi dagger. Shouldn't there also be a term? Shouldn't there be another term for to respect to psi and the time derivative?
That's a good question too. So the psi is complex, so it has both real part and imaginary part. They can be varied independent from each other. So you get actually two equations. And independently varying real part and imaginary part is actually the same thing as treating psi and psi dagger as independent variables. So I can take the variation of the Lagrange action with respect to psi dagger, and then requires the stationary with respect to the variation. That's one condition. And I can also take the variation with respect to psi that will lead to another Euler-Lagrange equation. That's yet another condition. And those two conditions end up being just the Hermitian conjugates to each other. So here I'm only writing the equation I got from varying psi dagger, but I get another equation by taking infinitesimal variation with respect to psi. And that Euler-Lagrange equation is just a simple Hermitian conjugate, or what I have right here. So this is the way you get two equations, but content of two equations are just Hermitian conjugates to each other. So if one is satisfied, the other is also satisfied. Does that answer your question?
Yeah.
Okay, good, Osher. Thank you. Any other questions?
Yeah, I had a question. So is you said the psi dagger x is the creation operator, and then psi just of x is the annihilation?
That's right.
Is that right?
Yeah,
okay.
That's right. So that's why I can use psi dagger x to keep adding particles to the system, because they are the creation operators. And once you have too many of those, you can use psi of x to annihilate one of them. And if you keep doing it, eventually we will remove all particles and revert back to this the vacuum state. If you act annihilation operator on that, then that turns into zero. Just like the ground state of harmonic oscillator goes to zero when you act the annihilation operator on it. Does that answer your question, Jacob?
Yeah, it does. And then so then you say psi of x is a quantum field. So you're saying that the annihilation operator is a quantum field, or both psi dagger and psi of x?
Yeah, both of them
you know what
are
I mean?
quantum fields. Yes.
Yeah.
Psi of x is a quantum field which represents annihilation of particle. Psi dagger of x is another quantum field that represents creation of particles, and both of them are quantum fields in the sense that they are quantum because they are operators, and they are fields because they are function of x. So here you have two quantum fields. One acts as an addition operator, the other that acts as the creation operator. So thank you for the clarifying question about this terminology. Any further questions?
So psi of x and psi dagger of x are sort of like, well, they're quantum fields, but they're sort of like eigenstates of A and A dagger.
No, psi is not a state, it's an operator.
Oh, okay. All right.
And you can talk about the eigenstates of this psi of x operator. And that is actually yet another coherent state. So we talked about eigenstate of annihilation operator in the case of harmonic oscillator, which had a good classical limit with minimum uncertainty. In the same way, we can also talk about the eigenstate of this annihilation operator or quantum field psi of x. And that actually ends up describing Bose-Einstein condensate of cold atoms, or superfluid of helium-4, or superconductor of Cooper pairs in a metal. And so it turns out that you can talk about the eigenstate of psi of x as well. But the distinction here is that psi of x itself is not a state, it's an operator. And that's a major distinction from quantum mechanics, where wave function psi of x represented a state. Here it does not. Psi of x is still an operator. You can talk about the eigenstate of psi of x operator, and that's the coherent state. We will talk about that, but that's separate from the operator. So I keep just emphasizing the same thing because that's a likely source of confusion. Psi of x is an operator. That's why we call that a quantum field, which is different from the wave function psi of x. Then you might complain, then why are you using the same symbol to confuse us? Well, it turns out that this is the standard notation in literature, so that's why I'm conforming to the standard notation. So I'm blaming the literature instead of myself to dig me out of the hole. But this is the reason why I'm using this notation psi of x. So thank you for the question, Natalie. Anything else?
In terms of our submission of stuff like homework, I would imagine that we might potentially return back to wave functions in the future. And since it shares the exact same symbol as this quantum field that we have here, how would we be able to differentiate between the two?
Yeah, so whenever I refer to a state, I use capital psi instead of a small case psi. So when you see a small case psi, that is meant to be a quantum field operator. When you see capital psi, that is referring to a state or wave function. And that's the way I'm trying to make the distinction clear. So hopefully that works. That's an excellent question too. And the submission of homework, please do that on B courses as a file upload. Any other questions?
I also noticed on the homework that it says it's due at noon on Fridays, but I think on B courses it says.
Oh no, that's a mistake. Then I must have screwed something up. I meant it after midnight instead. So I fixed the B courses to make sure that it doesn't show up as late. Sorry about that.
I don't think it will because it says 11:59 p.m. on B courses.
Oh, okay, that should be fine then. Yeah, good. Any other questions, either on this slide or about the homework submission? And again, I intend to post a new homework problem later today. Everything good? Okay, so now you have seen quantum field theory. Ta-da! So that's already a major progress. So we have actually constructed the Schrodinger field theory bottom up. So you are experiencing, sort of witnessing how the quantum field theory came about. But now we take the top-down approach. If you are given this Lagrangian, what are you supposed to do? And so if you're given this Lagrangian contains all information you need to see that psi of x ends up being the annihilation operator, and psi dagger of x ends up being the creation operator. So we constructed it. So that's why you now know that psi of x is meant to be an annihilation operator. But if the first thing you were given is just this Lagrangian, you wouldn't know that, right? So if you are given this Lagrangian, you go through the steps of coming up with a quantum theory and then figure out that psi of x has a role of being an annihilation operator. So the question is, how do you actually do that? Otherwise, 2 arrows don't meet in the middle. So we're trying to do this bottom up. Now we are trying to do this top down. So suppose you are given this Lagrangian. The first thing you do is to work out the canonical commutation relation. So if we have a Lagrangian, the derivative of the Lagrangian with respect to the time derivative of the coordinate is what defines the canonically conjugate momentum. And that's something you have done in harmonic oscillator on the second day of the class. And now we are doing this for the field theory. So I take the derivative of the Lagrangian with respect to the time derivative of the field. Now that's psi dot, thanks to Newton. And then what multiplies it, IH bar of psi dagger, then is its canonically conjugate momentum. So the way you set up the canonical commutation relation is that psi of x, that's the variable, and conjugate momentum, that's IH bar of psi dagger, is IH bar. But only when they are referring to the same position, in the same way that for the harmonic oscillator, they had to refer to the same site. Now that the space is continuous, this is a delta function instead of Kronecker delta. Then I cancel IH bar from both sides of the equation, and then out comes this commutation relation between psi and psi dagger. So that's how you obtain this commutation relation. And you define the Hamiltonian as PQ dot minus L. And PQ dot is the same as this form, PQ dot minus L. So that cancels the first term. And because it's minus L, it's flip the sign of the second term. So this is the Hamiltonian. And then you start checking that this actually has the correct behavior for a free particle. And that's what we want to achieve. So let's make sure that that is the case. And this commutation relation between x and psi dagger is now telling you that this is similar to the commutation relation between annihilation and creation operator, A dagger being 1. So you start to actually come up with an educated guess that psi of x is the annihilation operator, psi dagger of y is the creation operator. So based on that educated guess, you come up with this vacuum state, 0. You create one particle using this creation operator. Then I take the linear superposition of this state at position x by using this exponential factor, which I hope would represent a free particle with the wave number k. And then I like to verify that. So I act Hamiltonian on this state k. And that's something we have done with the lattice case before. Now we are doing this in continuum. And here I have an annihilation operator. Here I have the creation operator. So if I replace this by a commutator, the second part of the commutator has an annihilation operator acting directly on the vacuum state, and that's 0. So the second term vanishes anyway. So from this line to the next line, I did not change anything. And I'm still left with integrals over both x and y and all the other factors left in the expression. And if I take this derivative out of the commutator, then this is a psi dagger commutator, which we know is a delta function. So here we go, that's the derivative of the wave function. And then I do integration by parts in y to let this y derivative act on here. Then I get this. And I integrate over y using delta function. Now y integral is gone. The only thing I have left is x integral. Finally, I do integration by parts 2 more times so that twice this derivative on psi dagger, now I let them act on e to the ikx. And the derivative with respect to x pulls out ik from the exponent. So I get ik squared times minus sign. So that leads to h bar squared of k squared over 2m. And the rest of the expression is nothing but the state k. So now you know that this is indeed the state with the correct energy of a free particle, p squared over 2m. So this is the first step to verify that the Lagrangian we came up with, I don't know anything about how it had been derived now. Once you are given this Lagrangian, you just quantize it, and indeed you find a free particle state. So that's now the top-down approach. So on next week, I generalize this further, not just the plane wave state, to an arbitrary state you may have of these particles. And that's where I start making distinction between little psi, that's an operator, versus capital psi, that's a wave function. Then you start to see how they play different roles and to minimize the confusion that might happen in this quantum field theory for the Schrodinger field. So that's the plan for the next lecture on Wednesday, and I hope it's clear where we're heading. Okay, that's the end of the lecture today, and I'll stop here again and see if there are any questions. No questions? Okay, so as I said, let me check if Chris is willing to give discussion section on the Lagrangian Hamiltonian stuff, because not everyone has seen it based on the lecture note I posted already in B courses. And I also asked him if he's okay to have that recorded to be posted on YouTube later for those of you who cannot make that time slot for the discussion section. So I asked him to make an announcement if he agrees to do so. Anything else? All good? Okay, and have a good weekend.
Thank you.
Thank you.
Bye.